we will prove that the determinant of a product of matrices equals the product of the determinants of these matrices. Well, a proof consists of two parts. First of all, suppose that A inverse exists. So that A is actually an invertible matrix. Then look at the matrix A augmented with AB, and we calculate its reduced row echelon form. Then this equals the matrix IN, so the identity matrix. And on the right hand side, well, actually what we've been doing is multiplying on the left hand side with A inverse, so we get B. We know that A equals the number of -1 to the number of swaps we've been using times the normalizing scalars on the way. So these follow the Gauss-Jordan elimination steps. We know that adding multiples of rows to other rows has no impact, so we can characterize the determinant of A as such. So we know that the determinant of AB, since AB undergoes the same manipulations, is -1 SK1 times KP times the determinant of B, since AB is transformed in B using the same Gauss-Jordan elimination steps. Well, what it says here, we just plug in the determinant of A, which was equal to -1 to the power S with the product of the ki's, times the determinant of B. So that's one part. Now suppose that A inverse does not exist, which means that the determinant of A is equals 0. Then we are about to show that AB is not invertible. Well, why is that? Well, AB we're going to look at the original definition of a matrix product. The matrix product consists of, well, when we write B in columns B1 till Bn, then the matrix product is AB1 till ABn. So actually, the image of AB is contained in the image of A, since ABI are just a special combination of the columns of A. So the image of AB is contained in the image of A. But we know, since A is not invertible, that the image of A is not equal to the full space Rn, so neither is the image of AB, which means that actually that the kernel of AB is non-empty, is not a single vector 0, so this means that AB is not invertible, and since AB is not invertible, we have that the determinant of AB is 0, which then equals the determinant of A times the determinant of B, since the determinant of A is 0 as well.